Another type of calculation that we can do with this particular system is a time domain simulation. Okay, so this is one file that I have not presented yet. This is the file that gives the inputs as a function of time. So here it was indeed defined in the very same way as the harmonic spectrum, with a constant part and a sine wave with 1/2 of the Vs value, which is equal to just 1/2 at the fundamental frequency. Let's say, for instance, we would like to solve with a sampling period equal to 10e⁻⁶, which is actually 1e⁻⁵. The time span, I have defined it as something between 0 seconds and 4 seconds, minus 1 time the sampling period. This is not mandatory. This is just something that I do to match waveforms of collocation method and time domain methods. So they are synchronized essentially, but this may be clear after you use it a few times. I would like to initialize the time domain simulation from 0, but I could also initialize it from a point on the periodic trajectory described by this particular source, if it is available naturally, but I could also define it as the last point of a previous solution. We will try that later. I can define the absolute tolerance and relative tolerance of the time domain simulation, as well as the solver. As long as I am dealing with ordinary differential equations, I can use OD45, OD15S, OD23TB, and so on. If I have any delays in the system that I'm solving, then this option is disregarded and TDE23 is used by default. I suggest we just try running this and see the results. So as in the beginning of every run of the collocation method or every run of a time domain simulation, the toolbox begins with an update of the DSA structure in case any numerical values from the data file have been modified. There is some preparation done, and then the solver has started with ODE45, which is indeed what we had requested here. Some time has passed. It has taken about a bit more than 4 seconds to solve this. Then the command window shows that the solver is done, that input and output variables have been extracted, and also that Fourier analysis of the last fundamental period has been performed. This is the detail of this Fourier analysis, DFT being discrete time Fourier transform. We see that over the vector, the considered vector for this particular analysis, the one of the last fundamental period, a number of samples have been used. This is equivalent to a specific sampling frequency. We also know that since the fundamental frequency is equal to 1 Hz, and that we are also doing this Fourier analysis on one fundamental period, then the base frequency for this particular analysis will be equal to 1 Hz. However, since we have this amount of samples, or otherwise stated, this particular frequency, sampling frequency, we will have access to frequency information up to half the sampling frequency. There is also another Fourier analysis that is performed on the last XP fundamental periods. So if we look at it more specifically, at the time span, we have solved for a little bit less than 4 seconds, that is a little bit less than 4 fundamental periods. This is long enough to have this last fundamental period Fourier analysis, but also long enough to have a Fourier analysis over the last 3 fundamental periods. This allows us to have not a 1 Hz base frequency anymore, but a 0.33 Hz base frequency. We will see the results afterwards. So since we have run a time domain simulation, we have access to time domain waveforms. We have more of them, so we have time domain waveforms from the simulation, from time domain simulation covering one fundamental period. This is the last fundamental period, but also the last XP fundamental periods. So in this particular example, 3 fundamental periods, and also NP. Here it's actually covering the complete time span. If we have a look at this particular structure, we see that we have again a time vector and the vectors describing the time domain waveform of our 3 state and input variables. Likewise, I have access to the harmonic spectrum of these data structures. This is naturally something that I can find in the HD structure. As before, we see the results of the collocation method, which is still stored, but now we have additional harmonic domain structures which come from the time domain simulation. This is the harmonic domain data from the last fundamental period, the harmonic data from the last 3 fundamental periods. These ones are defined up to the maximum harmonic rank, which we had set to 1. So specifically, we would have this. Having set HM to 1, we have access to 3 Fourier coefficients. Naturally, we have more if we have a look at this one. So the same number of Fourier coefficients, but simply the base frequency is not the same. This one, FHD, is just the full harmonic domain data.